Hey there. I think we're live. I think it's working. Yep, it's working. Nice. Okie dokie here. Ugh, there's like a Gemini AI button in the top of Chrome now. Ugh. I'm aware it exists. I don't want to use it all the time, Google, or ever. Howdy, y'all. It's the Tuesday night stream. I have some calculus questions to answer. Oh, let me get. But first, let me say hi. My name's Ryan. I'm the calculus tutor. This is streaming homework help. I'm here to answer your math questions. I assume for many of you that will be questions from your math class, whether it's homework or test or quiz review, anything like that. Or you just you're struggling with a topic. You're like I panic every time I see fractions, and I don't want that to happen anymore. Can you help me understand fractions? Yes, yes, I can. Um, but yeah, mostly probably just like homework questions, things like that, or questions from everyday life. You're dealing with a situation. You're like, this seems like a thing that like math could help me with, and that maybe you don't feel confident about your ability to approach it fully mathematically, or you don't you feel like you don't understand all of the math involved, but you do think approaching it mathematically could be helpful. um, we can talk about it, and I can help you understand that math and feel confident about that math, and we can talk about your problem and explore it. And yeah, that's what this space right here is for all of you out there to say, hey, I would like some math help. And I am here to say, hey, I would like to help you with math. uh, the math that you need help with, whether that's because you have school, and school is giving you these math problems that they say you have to do, and you want to do them, but you're having trouble doing them on your own. Let me help. So how do you do that? How do you participate? Well, what you can do is you can go. Oh, normally I have my notes up, uh, and you can see right there. You can go to thecalculustutor.com uh, to submit your math questions. But let's say you do go to calculustutor.com. What will you see? This is what you see. If you go to thecalculustutor.com, this is the website you will find yourself at. Oh, wait a minute. Let me reload it. Aha. Now, this is the website you will see yourself at. Uh, Excuse Night stream yawns. Uh, there's a submit a question button right here in the little streaming section, so you can click that. That'll take you to the streaming page of my website and scroll you down to the submitting homework problem section. There is a homework submission form button you can click, or as you can see, you can submit your questions to Ryan at thecalculustutor.com. That's me at my website. Pretty straightforward. And because a email is just a blank like text box, here's sort of some guidelines for how to submit a good question. But we'll talk about those because I want to look at the form. I think the form is probably the best way to submit a question, but absolutely feel free to just send an email if that seems most straightforward to you, because that's the most important thing. So if you click that button, um, it should take you to this form. It may, before you see this form, it may ask you to sign into your Google account. You have to sign into a Google account because you can submit files, images specifically, so you can submit pictures of your homework, or your problems or whatever, whether it's quiz prep or whatever. Um, yeah, and so in order to submit files on a Google form, the people who are submitting it have to be signed into a Google account, which I sort of get. So yeah, so before you see this page, it might ask you to sign into a Google account. Because of that, if you sign in with, say, your school Google account, there is a chance that it might tell you, oh, you can't access this form because it's outside of your school or whatever. Um, if that's the case, I apologize. Feel free to either sign out of your school Google account, sign into your personal Google account, and access the form that way. That should be fine. If you don't have a personal Google account or you don't want to use it, again, you can just email me, ryan@thecalculustutor.com. Um, and I'm going to go through this form. Basically, anything I ask for in this form, try to include it in your email. Should be pretty straightforward. Um, my goal is for this to be a straightforward process. I want to get it as streamlined as possible because I don't want there to be I want there to be as little friction in the question submission process as possible. I used to, when I worked actually in a school building, when I was like a classroom teacher, I had before and after school drop in homework help, uh, that any of the students, not just my students, but any of the students could come and just get and ask questions about their math homework or whatever. Um, and it was super great. And once people found out about it, they used it, and it was really easy. And I'm trying to sort of emulate that same sort of thing, but online, and for all students. It doesn't matter whether you're at my particular school; everybody can access this. So anyway, I say all of that to say, if any of this feels like a barrier, do as much of it as is reasonable for you, but don't submit your question whatever way makes sense for you, and I will do my best to parse it and give you the best possible answer. Um, but yeah, so just walking through this form really quick, you have to check the box to say, yeah, this is my email address. Um, Then tell me who you are, just your preferred name. This is so because I'm gonna say who submitted the questions, right? So that you can hear when you're watching the stream, you can be like, oh, Ryan's about to answer my question. So I'll say, oh, this question was submitted by such and such. Um, so just tell me how you'd like me to refer to you. It doesn't have to be your real name. This would also be a good place to include your pronouns, if you care. Otherwise, I'm probably just going to use they. All right. Where did the question come from? This is another very quick one. I'm thinking just teacher and class. Mr. Anderson's Algebra 2, right? Uh, M- Mix Lancaster's Geostats. Boom. Just that's it. If it's not from a class, um, or if it's just tell me just very briefly, in a few words, where it's from in your life. Um, yeah, so that's again not meant to be barrier. Just that's just to help me get a little context, and also as I accumulate more and more questions that people have submitted, it'll help me organize them. Um, because chances are, if you're submitting a question, other people out there have the same question, they're just not submitting it. Um, so yeah, so there's those things, and now we get to the main part of this. Here's where you submit your question. However, this you don't have to retype the entire math question. That would be so tedious and such a pain in the butt. Uh, there is a place for you to attach files, and the idea there is that you will take a picture of the math problem and attach it and send it along that way. Which means maybe you do this form on your phone. You go to that website, thecalculustutor.com. You click on the button for the form and just go to it right on your phone. Then you can switch over to your phone app, take the picture really quick, and then click the add file button, and find it right there in your camera roll. Um, so if you're going to submit the questions with a picture, what is this section for? Well, this is a spot for you to help me uh, sort of understand what about that problem you're having trouble with. So this is just a place. So the key here, right, is a place for you to be as specific as possible. So you're just submitting, your entire a picture of your worksheet or a picture of your textbook page. Sure, I can see the problem, but that doesn't help me understand what the problem is, right? Uh, so that's what's going on here. Um, so here is a place where you could be like, oh, number 12. What's the issue with number 12? Uh, I'm having, oh, you can probably hear the typing sounds. I'm so sorry. Oop, there we go. Um, I'm having trouble with oops, I'm supposed to say with the graphing parts. Boom. That just helps me say, oh, okay. First of all, it's number 12, in case you do just send me a picture of your whole worksheet or your whole textbook page or whatever. So direct me to the particular problem and then a little bit more about what about that particular problem is giving you trouble. Now, maybe you're not even sure where, like deep into the problem, you might have trouble because your issue is that you're not sure how to even start the problem. You're not sure what you're supposed to do. Um, that you can tell me that. That's actually really great. You can literally just say, "I'm oops, not sure what this problem wants me to do." Right? That might seem like a cop out, but if that is how you're feeling, it's really not. That's quite specific to me. I understand that math problems sometimes are it's like, "What do you want me to do? Like, why are you asking it that way?" Because really, really, sometimes questions are just phrased bad. They're just constructed poorly. And if you could have somebody parse it for you and just tell you in a straightforward way, "Oh, they want you to figure this out." You'd be like, "Oh, okay, well, I can do that." Right? And so it's like none of the math is even actually getting in your way. It's understanding how the math is being communicated to you, right? And that's part of math, but like if that's the struggle, that's the struggle. So yeah, so this is just a place for you where you can direct me as best you can. Again, be as specific as possible. And like in both of these examples I gave, it was like I would say not even one full sentence. I didn't put a period at the end. But yeah, one or two sentences is all that this asks for, if even that. Um, we'll skip past this really quick to talk about the files again. The idea with the files is, yeah, you'll take a picture, and that way you don't have to retype the problem. With the pictures, two things to keep in mind. Make sure that pictures are clear and complete. So clear just means the text is readable. It's not too blurry, and I just mean too blurry. A little bit blurry is totally fine. It's super hard to take a picture of a lot of text and not have some of it be a little bit blurry, honestly. So yeah, just again, do your best. Make sure it's clear. Complete means don't accidentally crop out part of the problem when you're taking a picture of it. You get too focused on making sure the text is clear, and anyway, it's happened. Um, the other part of complete though is so make sure the entire problem is included in your image. You can also include more than one image, and why you might want to do that is because oftentimes problems in a textbook or on a worksheet, they have a separate block of instructions, right? Like, oh, here's the instructions, and those instructions are for these 6 problems, and then there's another set of instructions, and those instructions are for the 10 problems after them. So make sure your picture either includes those instructions, the instructions are visible in the picture of the problem, or take a separate picture of the instructions and also include that. Um, Also, for completeness, include any pictures or diagrams or charts or tables, anything like that. Anything else that make sure the everything that was provided for you to answer the question, let me know about it. The more I know about what about the context in which you're answering the question, the more helpful I can be to you. This includes, like, say there's a blank coordinate axis because it's like a graphing problem, right? And they just went ahead and gave you a blank coordinate axis. That's really nice, right? Um, make sure that's included. Either take a separate picture of it or it's included in your original picture, because I will use that in the notes and I will use that while I'm answering the question, so that the thing that I'm doing in the notes and on stream looks looks like what your teacher would expect from you. Like, that's going to be my goal oftentimes, is to try to at least explain, here's what I think your teacher's trying to get after. Here's why you're being asked to answer this question. Here's why this question is phrased this way. All that sort of stuff. I'm going to try to make the connection, right? I was a math student once. I was a math classroom teacher once. I've been a math teacher for decades of my life now. Um, and so I just want to help. I can be helpful in that way, help bridge that gap. Yeah. Oh, you can also include, so maybe it's not from your textbook, or it's not a physical worksheet, right? Maybe it's on Canvas, or it's web work, or it's My Open Math, or any of the Fuel Ed, any of you know, any other online homework place or math workplace. Take a screenshot and attach that. That's totally fine. If it's like a PDF worksheet, you can just attach the entire PDF. So you don't even have to take a screenshot of it. You can just download the PDF off of Canvas or whatever and just attach the whole thing. If you do that, it's even more important that you direct me to where in the PDF your question is. So probably tell me like what page it's on as well, um, because sometimes when teachers construct these PDFs, there might be a problem number 7 on the first page, but also a problem number 7 on the fifth page, or whatever, because they're sort of copy and pasting and mashing it together from different sources. Anyway, so yeah, uh, the very last thing you might include is a picture of any work you've already done on the problem. So if you did the problem and you got stuck, or you did the problem and you checked your answer and it's not the right answer and you're not sure why, um, or maybe you did another similar problem that you did work all the way through, but this one you weren't sure about. Basically, send, if you can, as one of the pictures you submit, if you give me a picture of some work you've done related to that problem, that can be really helpful for me. I can look at that and maybe see, oh, they sort of they did this thing that tells me they might have a misunderstanding about this, or I can see maybe you did something a long way, and I can be like, oh, it's actually a little bit easier if you do it this way, or whatever. Um, your seeing what you've already done can be really helpful for me to really try to explain and find out what's the thing that you're actually struggling with, because that's ultimately my goal. I'll work through the problem. That's totally fine. You could literally just send me the problem number, a picture of the problem, and I will work through it. But I won't know where to focus, right? I won't know what parts of it you in particular were struggling with. Now, I will know what parts of it many students might struggle with, in my experience, where where the common misunderstandings are, and maybe that's what, maybe you have one of those common misunderstandings that's messing you up with the problem. Um, but yeah, so yeah, the more you give me, the better my answer can be, is ultimately what it comes down to. But that said, don't let this be a barrier. I don't, you know, it it's kind of it feels like it would be unreasonable for me to expect anybody to spend any more than about 2 minutes submitting a question at the most, right? So yeah, I really want this to be quick and easy. Um, and if any part of it feels harder than it needs to be, tell me about it. Send me an email. Um, one last little piece, you might have saw this box here. It's an unchecked box. If you check it, you're agreeing, yes, you may share the images I submit of my own work on this problem. So when you submit work, any work you've done on a problem or a similar problem to help me, My promise to you is that will not show up on stream. That's just, you're sending that to me to help me best answer your question. But I totally understand and expect that most people would not want their math notes or math work or whatever um, to just be broadcast on the internet. Even though nobody watches these, I still wouldn't do it. However, for some students, especially students, in pre-calc or calculus or college, university level mathematics, those sorts of things, what they might be really helpful to them, and I'm totally willing to do, is go through the work they've done to check their work. And it's a lot easier to do that if I can just show it on stream. So I needed a way for people. The general promise that I'm committed to is your work won't show up on stream, unless of course that's what you need help with, is you need me to go through your work to check your work. That's literally what you're asking me for. So I just needed a way for people to communicate that to me, that like, yes, you can show my work, because what I would like you to do is go through and critique it, kind of like a art critique, or sort of like, check my process. I'm sending you the work I did on test review questions. Please will you go through it and see if my work looks correct? Like, oh, if there's similar questions to these, I'll do fine on the test. Anyway, that's a thing I can help with. And I needed a way for people to be able to submit that sort of thing. So simple checkbox, I think, solved it. For the most part, you can ignore that checkbox. If you send me a picture of your work to help me answer your question, my assumption is you don't want that to show up on stream. And that includes when you submit stuff in email. Also, attach pictures to the email, please, pictures of the problem, or screenshots, whatever. And if you include pictures of your own work through the email, again, my assumption is you don't want it to show up on stream. The pictures of the problems you send in, like from a worksheet or screenshots or whatever, those very well will probably make their way onto the stream, so long as there's nothing identifying in them. Um, and if there is, I'll get rid of it before it shows up on stream. Um, but yeah, those things will show up on stream because they'll just speed up my process. I will take the question you submitted and use that as the basis to spring off of to answer. But any work you submitted in addition to it, that'll just be on my other screen for me to look at. Anyway, you guys get it. That's how you participate. Pretty straightforward, I think. And as always, you can just submit questions by sending them to ryan@thecalculustutor.com via email, if that's easier for you. But the submission form button on the website is there. You can also submit more than one question. Absolutely. If it's the same, if it's a question if it's a group of questions that all have the same sort of set of instructions, um, you can submit those all together as a group. But if it's different problems that are asking for fundamentally different things, submit them as separate problems, because like there's just no overlap between them. Or even if there is a little bit of overlap, if the instructions are different, what you're expected to do with the problem is different, submit them as separate problems. But yeah, let's. Oh, these notes where I do the problem here. Um, you may have noticed it. I meant to point it out as we were going through the website. There is a button right next to the submit a homework question buttons that will take you to these notes. Um, so yes, you can see it on stream as I will work through it. I'm sharing my screen. You can see it, but as soon as I scroll off screen, if you wanted to see that again, there's no way on the stream for you to get to it. So you just go to the notes yourself, and you can scroll around. They're read only for you, but they're live, and you can watch in the notes live as I'm writing stuff down in real time. So that could also be a place, instead of following the stream, or you could make the stream real small and have this up. Whatever works for you. As people start to use this service, I hope to hear from people about how they use it, because that'll help me sort of optimize as well. But yeah, that is the homework help stream. Let's check for submissions. So none on the form. Looks like none in the email. Okay. Uh, I actually do have some problems though from a calculus student I'm working with. Um, so let's grab it here. Okay, here's our first question. Boom, boom, boom. Um, and then there's a little bit more with this. Let's go back and okay. So my student mentions a little bit finding the E confusing. This is in text, so I know they did a lowercase e. They're talking about this E right here, Euler's number. So before we look at this question, let's do a little notes, a little crash course on Euler's number, shall we? So breaking out the all right, Euler's number. So you all are almost certainly aware of numbers like pi, right? Uh, this right here, this is actually the Greek letter. This is pi, Greek. Oh my gosh, what was that, Nero? A Greek letter, which just means it's from, it's not from the alphabet, right? Which is our collection of characters that make up our language. It's from a different language's uh, alphabet. And actually an alphabet, right? They have alpha and beta. That's an alphabet. The Greek alphabet. We often in math adopt characters, symbols from other places because we need so many of them ultimately, right? Like the first of all, the 10 numerals 0 through 9, those are already taken. Those already have meaning. We can't use those for other things. Um, and then you have the 26 English alphabet letters, uh, 52 if you count uppercase and lowercase. So that's a lot. That's nice, but again, there's so many constants of nature, and then some of the letters get normalized to mean certain things. X is a very common variable. It also is the horizontal variable when you're working in a coordinate system. Um, so you don't really want to use X necessarily willy-nilly, though it is the one that you are allowed to kind of do that. R generally means radius. S generally means distance, or displacement rather. Um, right. And so we end up using them up. So we borrow them. So we had a number pi, which is approximately 3.1415 9 dot dot dot. That's yeah. And it keeps going forever, right? That's one of the things you learn about pi. It's this really special number that like goes its decimals go on forever and they never repeat, and they never end. Um, and yeah, and pi is this particular one, and pi has to do with circles. It's the ratio of a circle's circumference to its diameter, right? You take any circle, and if you perfectly measure its circumference and perfectly measure its diameter, every time when you divide them like this, you'll get pi, and that's all it is. It's the ratio of a circle circumference to its diameter. Um, it has all these properties. There's a ton of other numbers. In fact, an infinite number of them. Um, like this, they have decimals that keep going and don't repeat. Um, many of them we haven't discovered any particular use for them. Um, but one of those numbers is called E. We just use a lowercase e, right? So we used up one of the alphabet, one of our alphabet's letters E now, lowercase e, is now locked to this value. It equals approximately 2.712882. There it is. 828 dot dot dot, and it keeps going forever without repeating or ending. I guess that's what goes on forever means. But it never repeats, just like pi. But it's a different number than pi. Um, it's a pi and e, Euler's number, are transcendental number. Like there's all sorts of things that are special about these numbers. They're the same class of number. Um, and they just come from different places. Um, looking on the yeah, I was trying. So like here, sorry for zoning out for a second here. I was scanning through the Wikipedia, um, because I was blanking on like an easy to like explain uh origin of E, whereas like the pi is circumference divided by diameter is pi. There's actually other places in nature where pi shows up, other ways you can derive pi, and in fact, this wouldn't be a good way because you can never perfectly measure the circumference of a circle, and if the circumference of a circle was an exact uh, number of units of whatever arbitrary unit you're using, then there's no way its diameter could possibly be, and so again, you couldn't precisely measure it. Um, though as precise as you could be, that's how precise your estimate was for pi would be from it. Anyway, there's no simple little thing for that. For E, we've found it in a lot of different places. Um, it shows up if you analyze things like compound interest. It shows up, and it's fundamental to that process. Um, because um, oh, how do I explain this? Well, I will explain. I will write this down, and I won't explain it immediately, but it will make sense based on some of the other stuff that we're going to talk about tonight, based on these problems that we're going to look at. We can kind of come back to it and sort of retroactively make sense of this. I think one of the places, one of the definitions of it, one of the places it arises from, that is if you take one and you add to that 1 over um, some n value. And now you take all of this and you raise it to the nth power, right? So we're starting with this is why it shows up in compound interest. This is essentially just the compound interest formula, or at least a piece of it, the compounding part of it. So essentially what we're doing here is we're taking a number just ever so slightly bigger than 1, right? So that's why it's 1 plus is we want this number to be bigger than 1, but only a tiny bit bigger than 1. And so what we can do um is we could be like, okay, well, what if it's actually not a tiny bit bigger than 1, it's a whole half unit bigger? Then n would be equal to 2. So it'd be 1 plus, say, a half, so 1.5. And then, but what if we then square it? What happens to that number? 1.5 times 1.5, it's 2.25, as a matter of fact. It's like, oh, okay. Well, what if we get a little bit smaller? What if we do a third, right? So it's 1 1/3, or 1.33333 forever, right? Um, and we raise that to the third power. Now, why the reasons why we're doing this, why we're raising it, why we're not just doing this part, but we're raising it to a power, is because essentially here's what's happening is as you get closer and closer to one itself, right? So 1 1/3 is closer to one than 1.5, right? When you multiply that number against itself, it's a still smaller value. Well, it's bigger, but like it's a decreasing amount the first time. But if you keep doing it, it does get bigger. It doesn't matter how small a number is, so long as it's bigger than 1, if you raise it to a high enough power, it will still get huge. Um, and so we're sort of we have sort of 2 race conditions. We're racing towards 1, trying to get as close to 1 as possible, because 1, if you raise it to a power, it doesn't matter what power you raise it to, it'll always be equal to 1. 1 raised to the millionth power is still 1, because 1 times 1 times 1 times 1, it'll just always equal 1. So we sort of this race, as you race towards that identity value of 1, but not quite there, and as you race towards raising it to higher and higher powers, like what happens, right? And that might seem like a weird question to even be curious about. It arises when you're trying to calculate interest. Um, we'll get to that. I'm sure we are absolutely going to talk about interest and interest equations on this channel. So, um, oh, you wait for that. Anyway, if we take this and we make the in a bigger number, therefore this is 1 over n is smaller and we're closer to 1, but we raise it to a bigger power. So if we do that and we look at the pattern of what happens as you make n a bigger and bigger number. So that's what this LIM limit out in front here as n goes to infinity, all that's saying is, okay, what is this pattern? 1 1/3 to the third power, 1 1/4 to the fourth power, 1 1/5 to the fifth power. Is there a pattern there? Is each of those values getting closer and closer to something? And in fact, they are. They're getting closer to the number e. Um, cool. They had to get closer to, or they didn't have to get closer to something, but if they are getting closer to something, it has to be some number. And it turns out it's not a whole number. It's not a fraction. It's not right. It's not pi. It's not some other number we know of. It's this number. And then this number also shows up in some other places too. And so we're like, oh, are those ideas connected to each other? And in fact, yeah, they kind of are. But anyway, this is Euler's number. It is a an irrational, oops, transcendental constant of nature. Unlike pi, like circles sort of exist in the world, right? Like there's certain places that pretty close to perfect circles can form. And so you can sort of even if you're not doing anything to directly compute it, you can sort of see the ratio of a circle's circumference to its diameter just in the existence of the circle. And so pi is sort of something we can see in the natural world. E, it is a constant of nature, but it's a constant of like mathematical nature. E arises from uh, the sort of reality that math is like builds right from the mathematical fabric arises this particular constant. Um, and then of course, like I said, it shows up like we can apply those things like interest, compounding interest, um, to things in the real world. But that's all it is. E is I don't think we need to spend any more time than this on it. Um, Lowercase e, Euler's number, is just this, a constant of nature. It is just some number. You don't treat it any differently than you treat pi. It's not a variable. You don't treat it any differently than you treat 5. Anything you would do with 5, you can do with e or pi. You can multiply it, add it, subtract it, divide it, um, put in exponents, all that sort of stuff. Okay, so that's what E is, and my student was sort of asking about that. Um, so I will include a little note about that when I message them back. They were saying they were running into trouble when they treat it as a constant, but it is a constant, and so we're going to treat it as a constant. Let's get rid of that bottom part so we can just focus on A here. And let's get into this. Let's see what we can do. So this the title of this is L'Hopital's rule. There's a apostrophe there. Evaluate the following limits. All right. So I've already talked about limits with this student, so I know I don't need to review that with them. So I'm not really going to put much review about limits in these notes. For you all, it's just what we were talking about, right? The limit, so the limit as x approaches infinity, they're saying, what happens to this right here? What happens to the value of it as x gets to be bigger and bigger numbers? And we could just analyze this by hand by plugging in 1 for x and then plugging in 2 and 3. And when you just plug in bigger and bigger numbers, that would be really slow to do at 1, 2, 3, 4. We could do 1 and 10 and 100 and 1,000 and a million and see really as you, because we're going to infinity, right? A million is tiny compared to the numbers we can get to if we're pursuing infinity. And so we want to know, as x becomes bigger and bigger and bigger, what happens to this whole thing, right? There are a lot of ways to analyze limits. There's a lot of processes, and there are definitely rules and arithmetic around limits and things like that. I like to approach this from a very straightforward, logical standpoint. We're just saying this number is getting bigger and then seeing what happens. So this question is asking, what happens to 6 over e to the x minus 9 as x gets bigger and bigger? That's the question we're asking. That's what a limit is asking for. What happens to the expression, whatever expression follows the limit, as whatever limit it describes happens? Well, a place to start is go to the x. Well, as x gets bigger and bigger, the exponent of e to the x gets bigger and bigger. So what happens to e to the x as x goes to infinity? Well, e to the 1 equals e, which is approximately 2.72 e squared equals e times e, which is approximately, what is that approximately? Let's just do e squared. That is 7.39. Sure. EQ, which actually, here's what I'm going to say, which is greater than e to the first. E cubed is approximately 20.09, which is bigger than e squared. So we can say it appears e to the x also just goes to infinity. So we only plug 3 things in, right? So this could totally change, but it's a number between 2 and 3, and we're raising it to bigger and bigger powers. So it'll always just be between whatever 2 and 3 are at those bigger and bigger powers, right? E cubed is somewhere between 2 cubed and 3 cubed, right? 2 cubed is 8, 3 cubed is 27. 20 is firmly between them. And this will just keep happening. So yeah, it appears e to the x also just goes to infinity. So the limit as x goes to infinity of 6 over e to the x minus 9 is the same as the limit as x goes to infinity of 6 over x minus 9. Because the e to the x, that thing is also just going to infinity, right? Actually, you know what? This isn't actually strictly true. So I don't actually want to say that. I was going to kind of go in a simplification direction here, but let's not be simpler than this actually is, because it's actually not that complicated. So we don't need to artificially simplify this. Okay. Um um so yeah, so what can we do? Let's do my notes. So let's look at the next step of the expression. So the next step, so e to the x is the first thing that's happening to x. It's in the exponent of e, right? So it's telling us what exponent to raise e to. But the next thing that's happening after that is then we're subtracting 9. So we want to know uh, what happens to to e to the x minus 9 as um, as x goes to infinity. We just be subtracting 9 from a bigger and bigger number, right? So e to the x is getting bigger and bigger and bigger and bigger, right? Initially, when you subtract 9, e to the first, that's less than 3 minus 9. It's a negative number. Even e squared isn't even 7.5. So when you subtract 9, it's a negative number. But by the time we get to e cubed, it's 20. And so minus 9, that's a little bit more than 11. We're in the positives. And now everything after that, it's just going to be positive, bigger and bigger and bigger number, right? Um, so e to the x minus 9 must also grow to infinity. All right. So we can see the entire denominator is getting bigger and bigger. That 6 or that e to the x minus 9 is actually just as x gets bigger. So the pattern here, and that's what limits are. Limits are all about what is the pattern. Is there some fundamental value it's headed towards? Like we talked about with that definition of e, there was a fundamental value. It didn't just keep getting bigger or getting smaller. It headed towards a specific value. The and so that's sort of what we're asking here. Um, all right. So then let's look at the last step of the the expression. So what I'm trying to do here is show how uh, limit analysis is a process of sort of making your way through the expression step by step and seeing what happens. What would happen to this little piece if x got really big? Oh, it would get really big too. Okay, so we have something that's getting really big. What happens if you subtract just a number that's not getting bigger or smaller, just 9 or whatever, from a number that's getting bigger and bigger? Well, the result of that would also get bigger and bigger. It's just 9 less than e to the x is, but e to the x is getting really big, so it'll just be a little bit less than really big. Right. So remember, e to the x is going to very quickly get to a million and a trillion, and just numbers so big we don't have names for them. And so, what's 9 less than a trillion? Well, it's still basically a trillion. Um, right. So that's what we're dealing with. All right. So then let's look at the last step of the expression. Right. So this is and I want to pull it up here so I can make sure I'm looking at it's 6, yeah. 6 divided by e to the x minus 9. We already know the denominator is growing to infinity. So what happens when you divide 6 by bigger and bigger numbers? Right? Let's see. We do 6 divided by 1. That's 6. 6 divided by 2 is 3. 6 divided by 10 is 0.6. 6 divided by 100 is 0.06. 6 divided by, I could go to 1,000, but let's go bigger. Let's go 1,000,000. That's going to be 0.23456. There we go. So we can see the whole fraction is getting smaller because the denominator is getting bigger. Boom. Okay, so because the denominator is growing, we're dividing 6, a number that's always the same size, it's always this many. We're dividing that into more and more groups or more pieces. So each of those pieces is going to have to be tinier and tinier and tinier, right? Because there's only so much to go around. And that's the fundamental pattern here. We can see, so we followed that limit through, and we can see that that meant the whole fraction had to be blowing up. Or sorry, the whole fraction had to be collapsing down. The denominator's is the thing that's blowing up, and that causes the whole fraction to collapse down. And now here's a clarification I really want to make. Maybe you've already noticed this, but I want to make sure. Notice the fraction will never be negative, though. After or for x greater than 2. For x greater than -3. Okay. So the fraction, it's getting smaller and smaller, but it'll never be negative, right? So it's not becoming lesser and lesser, it's literally getting smaller. Smaller, but never negative means it's headed to 0. So here's the punchline. The limit, the limit as x goes to infinity. So as x becomes a bigger and bigger positive number, it always heads in that direction. So if we know that's true, then the expression 6 over e to the x minus 9, that has to equal 0. And there we go. So what do we do here? Actually, we can just look right here. How do we evaluate this limit? And this is the thing, I wrote it all down, right? But you can do this, you could easily do a problem like this in your head with no work to really show. We know x is going to infinity. The limit part is not a part you have to solve. It's information. It's true. X is always going towards infinity. So that's the pattern it's following. It doesn't really matter how fast it's going or whether it's doing it at any particular cadence, right? We just know because we're looking at, okay, if you plug in a bigger x value, if you follow that pattern, what does that fundamentally mean is going to happen here? Because this would have to follow some sort of related pattern because x is in here. Anyway, so okay, if x is getting bigger and bigger and bigger, e to the x is getting bigger and bigger and bigger, which means e to the x minus 9, which is 9 less than e to the x, but since e to the x is getting bigger, if you just do 9 less than bigger and bigger and bigger is just bigger and bigger and bigger, right? So the entire denominator is getting bigger and bigger and bigger. So you're taking 6, a number that is staying exactly the same size, and dividing it into more and more pieces. So each of those pieces has to be smaller and smaller and smaller. So the whole fraction is collapsing down. And in fact, it's headed toward the limit is 0. It will always, the bigger x gets, the closer that fraction will be to 0. You want the result to be a little bit closer to 0, make x a little bit bigger. You want it to be even closer to 0, make x a little bit bigger. The bigger you make x, the closer the value of the fraction will be to 0. And there we go. That's the process. So the limit, so this expression doesn't equal 0, but the pattern it follows is equal to 0. Or the place it's ultimately headed towards, even though it'll never get there, though. That's the other critical thing. It will never actually get to 0. That's an important note. Of all values it will attain. This is part of the reason limits are weird, man. And I don't think we just don't pause long enough on how weird limits are when we're teaching them to students and what a fundamental shift they are. The limits are the reason I tell students that calculus is kind of a shift in how you're approaching math. Up until you get to calculus or pre-calculus, you're focused on function value, and once you get to calculus, you start focusing, or as you're headed towards calculus, you shift your focus to function behavior. Limits are all about function behavior. They're not about what any one thing that's true for any particular x value. They're about observing a pattern and sort of extrapolating out and then identifying sort of a bounding value, a number that it is either the smallest or biggest number it ever will get to, or in the case of zero, zero is the largest number that 6 over e to the x minus 9, it's the smallest number that it will never get to at a certain point after x is anytime after x is equal to 3. Because there's a little period before that where you actually no, it could never actually be equal to 0, but anyway. So that's the idea there. Let's look at the next. There's a part B to this. Um, Can I? Aha, paste. Haha. Okay. So let me get my scale all back to normal. Okay. So this one looks really, really similar to the previous one, right? Have you found the difference yet? It's right there. It's a negative sign. The difference. Actually, let's put that underneath. The only difference from... Okay. So there's that. So that's our only difference there. So we're going to do the exact same thing, right? So what happens to e to the x as x goes to negative infinity? Okay, now negative infinity, similar idea to last time, it's becoming bigger and bigger numbers, but they just happen to be negative, right? So instead of going 100 and eventually 1,000 and 10,000, it's negative 100 and negative 1,000, negative 10,000. Those directions should probably be switched for you. They made sense to me, but the limit as x goes to negative infinity of e to the x is the same as the limit as x goes to positive infinity of e to the negative x. That's true. I don't think that helps make this clear, though. I could, if I was just writing a paper, that's probably the route I would go. But because I'm explaining this and trying to make some notes for a student to try to build some understanding from, um, I think that's more tedious than it needs to be. Okay. Um, so let's rewrite this as x becomes bigger and bigger negative numbers. numbers? Well, e to the negative x is equal to 1 over e to the positive x. So we can think of this, all the negative is doing is it's just causing the e to the x to flip into a denominator to be divided by rather than multiplied over and over again. Um, so this right here. Okay, so what we can say is similar to part A, as the denominator gets larger, the fraction becomes smaller. So e smaller, heading ultimately to 0. So as x goes to infinity, or negative infinity, e to the x goes to 0. Next step, e to the x minus 9 as x goes to negative infinity. Since the e to the x goes to 0, this becomes 0 minus 9, which equals negative 9. So as x goes to negative infinity, e to the x minus 9 goes to negative 9. Last step. So now we do 6 over e to the x minus 9. As x approaches negative infinity. E to the x minus 9 is headed to negative 9. So the expression becomes 6 over negative 9, which equals negative 2/3. All right. I don't need to do that on this screen. I can do my processing on my other screen. Go bundle it all together. Lock it up. Boom. Okay. We're actually getting a little bit low on time. I'm going to try to get faster at working through these types of problems. But so there you go. Limits are all about just working through the expression sort of step by step, seeing what would happen as that limit holds true. There's other techniques, but this is the best place I think to